My name is Chikage Fujikawa from Chuo University in Japan. I'll make a presentation on this title. Here is the outline of my presentation. First of all, introduction. Lately, various environmental surveys have been conducted on the moon. However, very little underground exploration has been done. The underground exploration can contribute to these three things. Therefore, JAXA has set these two as exploration goals. Considering the transportation costs and safety, unmanned small excavation robots are required. As shown in Figure 1, several drilling robots exist. However, these robots aren't capable of deep excavation because they move forward while rubbing their bodies against a wall, and they cannot discharge soil out of a hole. To solve these problems, we developed an excavation robot based on earthworm locomotion. As shown in Figure 2, earthworms move forward by peristaltic motion. The motion has these advantages. Therefore, we believe that our developed excavation robot LEAVO can achieve deep excavation. The robot LEAVO consists of a propulsion module and an excavation module. As shown in Figure 5, each propulsion unit extends and expands so that LEAVO can move forward while grasping the wall. As for excavation module, an earth auger, which is a drilling tool, rotates, excavates the ground, and conveys the soil from back to the body of the robot. LEAVO has two exploration goals, which are burying environmental survey sensors and collecting regolith samples at the same depths. To achieve these goals, LEAVO is required to perform vertical bending and horizontal excavation. In our previous study, LEAVO has successfully drilled 938 millimeters vertically. In addition, a flexible auger has developed for bending excavation. However, an existing propulsion module cannot bend. Therefore, in this study, we propose a flexible propulsion unit using Braid mechanism to replace the existing one. In addition, we model the grasping force of the unit and conduct a gripping force characteristic experiment to demonstrate the usefulness of the prototype and verify the modeling. Next, I'm going to talk about proposed method. First, as shown in Figure 7, the Figure 7 shows the schematic diagram of proposed propulsion module. The grasping part adapts a structure called Braid, in which fibers are woven into a lattice pattern, and each fiber is helical. In addition, we believe that moderately flexible and rigid fibers can enable sufficient grasping of curved and uneven wall. Next, I'm going to explain the modeling of gripping force. The purpose is design and control the Braid propulsion unit. Figure 8 illustrates the model, and the proposed unit is modeled as a thin wall cylinder for the sake of simplicity. And Table 1 shows the parameters of the model. In Figure 8, the compressive force and the external pressure from the wall cause the unit to expand, decreasing the height by delta and increasing the diameter by delta d. At this time, equation 1 and 2 are obtained. And then there is no external pressure. Equation 3 and 4 hold. Here, Young's modulus and Poisson's ratio can be determined experimentally from equation 3 and 4. The external pressure P can be expressed by equation 5. As shown in figure 9, the proposed unit pushes back the wall. So if we defined the vertical combined force that half wall receives as the gripping force, it is given by equation 6. Therefore, the gripping force can be derived from the compressive force and its dimensions. Next, let's move on to the gripping force characteristic experiment. We conducted the experiment to evaluate the modeling,'s validity and the usefulness of the proposed propulsion unit. As an initial step, the prototype was made of polypropylene bands, and the prototype can contract and flex like this. First of all, we determined Young's modulus and Poisson's ratio of the unit by placing weights on the prototype and measuring its dimensions under no external pressure. From the values in table 2 and equation 3 and 4, the two were these values respectively. Next, figure 11 illustrates experimental setup. The prototype was set in the center of the measuring jig, and the weights were placed on the prototype. Each grip force was measured 10 times with a force gauge. Results and discussion. Figure 12 shows the relationship between gripping force and compressive force. The lines and markers indicate theoretical and experimental values respectively. Please look at the yellow ones. After the unit touched the wall, the experimental values of gripping force increased as the compressive force increased. The obtained results indicate that the experimental values generally follow the same trend as the theoretical values. In addition, the prototype was made of the bands, which was woven by hand, so the uneven manual weaving causes the tilt of the prototype, as shown in figure 13. So we consider that the tilt led to a decrease in the experimental gripping force. Lastly, conclusion. Summary is as follows. Future works, we will conduct some experiments on gripping force characteristic for various hole diameters, and we will examine adapted fibers, fabrication method, and shape. Thank you.
Thank you for nice talk. So how about the gripping force in the situation of mixed materials?
Mixed.
So with big diameter sand and so small diameter sand.
Could you rephrase that, please? What's the situation mixed?
So mix means that so has a big sand and small sand. Mixed conditions.
Mixed sand?
So in this result, so using the same type, same diameter sand, right?
Yes.
Ah.
No, we didn't use sand.
So using same diameters materials?
No, we used the acrylic pipe
Acrylic pipe?
as a jig, as a measuring jig.
So, okay. Yeah, okay. So let's discuss after. Thank you very much.
Thank you.
So could you got these bands, right? How are you fabricating?
By hand. Yes.
It's a lot of work.
Yes. It takes time.
Do you anticipate needing to have a protective shell around the braid for actual digging?
What does put in?
Oh, like in the future, when you deploy this in sand, are you going to need like a rubber sleeve to protect the braid from scraping on rocks?
Yes. We need it to protect sand inside.
Do you think that'll affect any of the mechanics?
In our previous study, we used the rubber to protect the robot.
Slowly trying to speak us back on. But not good.
Why did you decide to use a woven structure instead of simple straight bands actually? So does it have to do with any McKibben shenanigans or?
Okay. Actually, we have another excavation robot, which is used under the sea, and its propulsion unit consists of artificial muscle. However, we cannot use it on the moon because of the serious environmental and it costs transportation costs. So we proposed this one. Does it make sense?
Yes, thank you.
Thank you.